For homework, we worked on problem 1.1 from our textbook, and the question was prove that any finite graph, in any finite graph, the number of vertices with odd degree is even. So this is a graph theory problem, and we're going to walk through one way of solving this problem. Now, to start with, let's just inspect the problem. The problem says first prove. Now, typically when we see something like prove, it means that we need to do this very formally, very, very precisely. We're not going to do it so formally. We're just going to make a strong argument, right? So we're going to skip writing everything down in detailed mathematics, but I'll present the argument to you here, which is the same thing that you need to do for your homeworks. Now, what are we trying to prove? That in any finite graph, again, our graphs are something like this, where we have nodes and edges connecting our nodes. We want to prove that in any finite graph, the number of vertices with odd degree is even. So let's review again, what does it mean for a vertice to have an odd degree? So nodes, vertices, the same thing. And we can connect these with edges. Now, the degree of a node is how many edges are coming out of it. So here we have one edge coming out of this node. Here we have 3 edges coming out of the node. So the degree is 3. Here, for this node, we have 2 edges coming out of the node. So the degree is 2. And here we have 2 edges coming out of the node. So the degree is 2. Again, the degree of a node is how many edges are coming out of that node. So we want to prove that the number of vertices with an odd degree is going to be even for any graph. And we saw this in this example here. There's 4 total vertices, and the number of vertices with an odd degree, we've got a vertice here with an odd degree and a vertice here with odd degree. So we have 2 vertices that have an odd degree, and of course 2 is an even number. So, okay, we saw one example where this property is true, but how could we make an argument that this is going to be true in general? So I'm going to start by thinking about the sum of all, the sum of the degrees of all nodes. So I'm going to look at all the nodes we have, and sum up the degree of all of those. And eventually I'm going to get to the argument that that we want up here. So the sum of degrees of all nodes, I am going to say that this is actually an even number, and in fact it's exactly 2 times the number of edges. Now, how do I know that? Well, let's take a look at an example. So if I have 2 nodes, then I can draw an edge between that. And the sum of the degrees of these nodes, we've got degree 1 and degree 1, the sum is 2. Okay, and if I add another node here, add another edge, now the degree of this is going to be 1, the degree of this is going to be 2, and the sum again, 1 plus 2 plus 1, it's going to be 4. That's an even number. And so what you'll sort of notice here is that every time I add a new node, I'm adding to the degree on both sides. Right? I'm adding 1 on this side and 1 on this side, which means every time I add a new edge, to my graph, I'm adding 2 to the sum of the degrees of all nodes. And here 2 plus 2 plus 3 plus 1, this is the sum of the total number, total degree of all nodes. This is for 8, right? So the reason that this is true, the sum of degree of all nodes is 2 times the number of edges, is because every edge adds 2 degrees across the entire graph. It adds 1 degree to the first node and 1 degree to the ending node of our edge. And of course, 2 times any number is going to be even, And so the sum of degrees of all nodes is even. Okay, good. Now, with this, let's break this down. So far, we've been talking about all of the nodes, but I'm going to break this down into the sum of the degrees for nodes that have even degree and the sum of the degrees for nodes that have odd degree, right? All nodes can be broken into two chunks. I'm going to break my set of nodes into two chunks. I've got the ones on the left here, which have even degree, and the ones on the right here, which have odd degree. Similarly, I have the nodes that have even degree on the left and the nodes that have odd degree on the right. What I'm saying is that the sum, the sum of the degrees of all nodes is going to just be the sum adding both of these numbers together. Okay, good. Now, what do we know if we have a even number here and we're adding two numbers to get an even number? There's two situations that we might be in. Either the component numbers are both even, that will give us an even number, or we're adding together two odd numbers, and that will give us an even number, right? That's the only way that we're going to get this top number to be an even number. So, right, if we had an even number and an odd number, then it would be odd, or odd and even, then it's going to be odd. So these are only two options that we could have. And I'm going to say that the sum of the degrees for nodes that have even degree, this is going to be an even number, and I know that for sure. How do I know that the sum of the degrees for nodes that have even degree is an even number? Well, I'm adding up the degrees for nodes that have an even degree. So I'm adding up the degrees 2 and 2 for the nodes that have an even degree. So I'm going to be adding up, doesn't matter, 2 and 2. And that's going to give me 4. And no matter how many nodes I'm adding up, I'm always adding up more even numbers. So I'm adding up more and more even degrees. And no matter how many even numbers we add, we're always going to end up with another even number. And thus we know that the sum of the degrees for nodes that have even degree must be itself an even number. Now, from the fact that this is an even number, we know that this number on the right must also be an even number. Right? So the sum of degrees for nodes that have odd degree must also be even, because we have to combine two even numbers to get this even number up here. Okay, now this is a sum that adds up. We're going to add lots of things together, and we're going to get an even number out at the end. So going back to our example, we're going to add here, we're going to add 3 and 1, we're going to get 4, and that is indeed an even number. Now, what can we notice? We can notice the same sort of thing here. If we were to add an odd number of nodes, of the degrees of nodes up, for example, 1, 5, and 9, a sum of an odd number of odds gives us an odd number. It's starting to sound like a tongue twister, but if we were to add an even number of odd numbers, we're going to get back an even number, right? So we must, if we know, right, we know that this must be an even number, because the left-hand side is an even number, and that's the only way the top one is going to be even. We know that we can't have an odd number of nodes that have odd degree here, because otherwise this would be a red box, but it's a green box. So this must be an even number of nodes that have odd degree. And will you look at that? That's actually the proof that the claim that we wanted to prove up here. Prove that in any finite graph, the number of vertices with odd degree is even. This is what we've done. The number of vertices with an odd degree must be even, such that we can propagate that evenness back up this sort of tree-like structure.